right, so what we're going to do now is we're going to explore what is called parent functions. And it's not an incredibly exciting concept, but I hope that when we're done that I've convinced you that you need to know them. Okay? So let's start by talking about what we need here. We're going to identify the name and the format, really just the formula for each parent function. We're going to know each graph, hopefully by heart, and we're going to be able to identify the domain and range for each. And again, this is not something that you want to just write down and forget. This is knowledge that is going to help you solve multiple math problems in the future by just understanding what a parent function is doing for you. Well, let's get after it. Sorry for the first 10 or 11 slides. They're not incredibly exciting, but I'll try to explain it out. So here's the first one. This is called a constant function. Constant simply means a number. So let's think about what that formula could be. F of x equaling c. That's the formula. We don't want to write f of x equaling 5 or f of x equaling 2. C is any real number, but this is the form. F of x equaling c. Let's see what the graph looks like. Well, if f of x equals a number, the graph is a horizontal line through that number. So let's just put it over here and say it is a horizontal line through C. Now, there's only two things left to do. We want to be able to look at this graph and say, well, what is the domain? So this is what I hope that you can get. If you know the wording, the form, and the graph, the domain and the range are something you don't have to memorize. It's something I hope you can just look at the graph and pull that information from it. So if I was looking at this graph, what domain is really asking is what x values are on this line. Well, they're all on this line. I mean, every single x value on the planet. This thing goes to the right forever, goes to the left forever. Domain is all real numbers, negative infinity to infinity. If I understood what range was asking, just asking what y values are on this line, well, there's only one. Every single coordinate is going to be something comma c. Like this is 2 comma c, 4 comma c, and negative 2 comma c. The y value is the same. It's a horizontal line. It is no different than writing y equals c, so the range is simply c. Okay? Now again, if we can graph these and you can read the domain and the range from a graph, these are things you do not have to know to memorize. We do want to be able to write this and understand what it looks like, and then from here we can always pull the domain and the range from our artwork. So let's do another one. This is called the identity function. So again, this is something we want to know. We want to be able to say the identity is f of x equaling x. Again, also no different than writing y equals x, but since we're dealing with function notation, we're going to say f of x equals x. So what's that graph look like? Well, it's right there. If this was y equals x, it means that every number that equals x also equals y. So let's think about it. If I threw in an x equaling 1, y value would also be a 1. So that's 1, 1, 2, 2, 3, 3. I go over to negative 3, negative 3. So that is called the identity function. And again, if I can graph this, I can say what x values, if I'm thinking domain, what x values are on this line? Well, it looks like it's going up forever and down forever, but it is also traveling to the right forever. It is also traveling to the left forever. It is every x value in existence. It is all real numbers. And the range, well, what y values? Well, it's all of them. This thing is rising forever. It's falling forever. The range is also all real numbers. And there's only one left that's it's not kind of, it is exactly linear, and it is called the linear function. So this is really the other forms. This is a parent function that is not horizontal. It's a parent function that's not the identity. So that's f of x equaling mx plus b, where b is the y-intercept and m is the slope, and the graph would just be some linear line somewhere other than horizontal or the identity. Okay, so there's a random linear equation that would be represented through mx plus b. And again, if I want its domain and I want its range, we can just look at this and say, what x's are on this line? Well, they're all on the line. So it's all real numbers. And of course, this thing would rise and fall forever. So the range is also all real numbers. Okay, let's do the squared function. This is our quadratic equation. Now, again, the reason we're learning these parent functions is because every single quadratic equation in existence is a transformation of this function. So we need to know what this one looks like. So let's graph it, and it's right there. So we get that parabola. If think about throwing in a 0, you get 0 squared, so we get 0, 0. 1 squared was 1. 2 squared is 4. Negative 1 squared was 1. Negative 2 squared was 4. So there's that parabola. Again, if I was looking at this graph and thinking about what x's are on this line, well, it is slowly traveling to the right forever, but it is still going this way forever. It is slowly traveling to the left forever. It is all real numbers for domain. The range, however, is not. Notice there is no graph down here. These are the negative y values. So the range has to be from 0 to infinity, and we get to count the 0. Remember, we can throw a 0 in and square it. So we're going to do a parenthesis on the infinity, but a bracket on the 0. So there's the range, 0 to infinity, which is a fancy way of saying the positive side of the y-axis. But we get to include the 0. Okay, let's look at the cubic function. Cubic function is exactly what it sounds like. It is f of x equaling x cubed. And now let's graph it. This one's got a little bit of goofy swirl to it. It's going to start down here and kind of swing through here and go that way. And we're really just after how does it behave? Well, it starts down here, it goes this way. It's got that little swirl. This one only has 1 0. It's going to be at 0. And if you try to cube, or 1 to the third power is 1, you go over to the 2 and you put a 2 in there, you're going to get 2, 8, -1, -1, -2, -8. So there's that graph. And we can look at this and say, and it looks like it's getting fairly vertical at some point, but it's not. It is still going to travel this way forever. It's going to go down, but also travel to the left forever. Domain is all real numbers. We can see it's every y value up here. It's going to include every y value down here. The range is all real numbers. Okay, now let's do some radicals. So the first radical is a square root function, and that's exactly how it sounds. It is f of x equaling the square root of x. This is the parent function for all square roots. And what does that look like? It's right there. Notice it can't be over here because you try to throw in a -1, well, you get an imaginary number. So although real numbers, the graph really exists where there's only real numbers, and that's going to be from 0 to infinity. So that's the domain. Again, this thing is going to only incorporate the positive y values. Again, we get to include 0, so the range is also 0 to infinity. And again, think about taking any coordinate along this line. All these coordinates would be positive x's. All these coordinates would be positive y's. Don't forget to include that 0. Okay, so let's look at a different radical, cube root, and that is again how it sounds, f of x equaling the cube root of x. And let's see what that graph looks like. And I just want to remind you that the cube function kind of did this. This was the x cubed. So if it's a cube root, it's actually going to come up from over here and go this way. And if we took a few numbers in there and threw it in, you get 0. The cube root of 0 is 0. So we still have a point at 0, 0. Take a 1. 1. Cube root of 1 is 1. The only difference is we're going to go out here to 8. Cube root of 8 would be 2. It would be up here. And cube root of -8 would be -2, et cetera, et cetera. So there's the graph. And if we looked at this and said, well, what x values are on it? Things going to the right forever. It's going to the left forever. Domain is all real numbers. And it does look like it flattens out, but it won't ever flatten out. It will rise very, very, very slowly, and it's going to fall very slowly. So the range is also all real numbers. All right, let's look for the absolute value, also called the V graph. So f of x equaling the absolute value of x. Again, all absolute value functions are going to be a transformation from this graph. So it's important to know what it looks like. And let's graph it. So there it is. Again, if we tried to throw in some numbers, the absolute value of 0 is 0. Absolute value of 2 is 2. We jump over to a negative number. Absolute value of negative 2 is 2. So what we're recognizing here that was we can throw in any x number, which is all real numbers, but it's not going to spit out any y value. It's only going to spit out the positive y's, but let's not to forget 0. So there is the domain and range of the absolute value parent function. Now the next one is one you may have never seen before. It's called the reciprocal. So f of x actually just equals 1 over x. This is the standard form of writing it. I put equaling x to the negative 1 just because they are equivalent. I didn't want anybody to maybe get mixed up. They are the same, but this is the standard way of writing the reciprocal function. So let's look and see what this graph looks like. But before I show you the graph, I want you to think, what can x never be? Now we've talked about domain restrictions in this class already. So what is the value of x that could not exist here? And hopefully you would come up with 0. This could never be 0, which means this graph I'm about to show you will include every x value except 0. It looks like that. 0 doesn't work, but every negative value will work, and every positive value along the x-axis will also work. So 0 is the only one we don't get to include, which means the domain is negative infinity to 0. We don't get to include the 0 with a union of 0 to infinity. So this is basically saying every number on the planet except 0. Now, this is called a vertical asymptote. You'll learn that in a future lesson, but that's what it's called. An asymptote is a line a graph tries to reach, but is never successful. It looks like it's on the y-axis, but it's never actually going to reach it. It's going to try its hardest, but fail miserably. Same thing with the x-axis. This thing's trying to get to the x-axis, but it's never going to reach it either side, which means the only y value we don't get to include is also 0. So there's the range of the reciprocal parent function. Okay? And the last one you would not find in your book, I've included it because it shows up quite frequently in, say, a calculus class, and it doesn't hurt to get a jump. Most pre-calculus students are only in that class because they're going to be a calculus student at some point. So let's throw in the reciprocal squared function. And all that really means is we're squaring the reciprocal graph, which would produce 1 over x squared, or x to the negative 2. Again, this is the only place your domain restrictions live, and the only thing this could never be is 0. So that graph looks like that. It's trying its hardest to get to the y-axis from both sides. It will fail miserably, which means every x that's positive works, every x that's negative works, but 0 does not. So there's your domain. It is the same as the reciprocal. However, if we look at this graph, we can see that the graph does not exist down here, which means there are no negative y values, but it is also not going to include 0. So range is 0 to infinity. It's from here up, not including the 0. Again, we're parenthesizing the infinity because we don't get to include that number either. So every number between 0 and infinity is along this graph for the y values, except don't include the 0. Make sure you're not bracketing your parenthesis. All right, so there's 10 parent functions. Now what I'm going to do is I'm going to go kind of hog wild here, and I'm going to give you 2 examples that are going to kind of talk about some futuristic things, some past learning that maybe you learned in Algebra 2. But all I'm really trying to do is show you the power of a parent function in a different problem, and why you might want to learn these versus just write it down and forget about it. So let's look at an example. So we already talked about the squared function. So there it is. f of x equaling x squared. We identified the domain was all real numbers, and the range was 0 to infinity. But let's just say that I was, and remember, I said every single quadratic equation is simply a change of this graph. So let's do an example here of saying f of x equaling x minus 2 squared minus 3. Again, this is a quadratic equation, which means this is a transformation of this graph right here. And all this is saying is I'm going to take this graph, I'm going to move it to the right 2 places, and I'm going to drop it 3. So if I move that to the right 2 and down 3, it would end up right there. Now, because I know what the parent function looks like, and I knew something about domain, the domain of the change is still going to equal the domain of its parent function. Think about this thing went to the right and left forever. Domain was all real numbers. If I take this and move it to the right or the left, I don't change that at all. So the domain of this graph is still all real numbers. But the range is not the same. The range was 0 to infinity. But notice I'm moving it down 3 places, which means these are now the y values that are included in this graph. So the range would be -3 to infinity, and we get to account the -3. So you'll learn this is a transformation of this parent function, and a vertical shift changes the range. But we wouldn't be able to do that without this knowledge. Now this one's a little bit crazier. Kind of, I said hog wild, and I was really talking about this one. So let's just talk about the cube function. We already have that. I just kind of put its domain and its range up there. But in this case, I'm not going to transform this. I'm going to take this more or less into a math problem that we just kind of walked away from. So let's just say that I have a third degree polynomial, because that's what the cubic function is, but I change it to a different third degree polynomial. And I've even thrown in an inequality here to get really crazy. So this is a third degree and this is a third degree. All I know at this point, before I do anything, the only thing I would truly know is that this graph, the behavior of this graph, will have some resemblance to the behavior of this graph. So since this graph is right here, it's coming down from down here and it's going up and through, I would say, well, it's only crossing the x-axis in one place. That's the parent function, because this can only be 0 in one spot. But if I took this graph, and I'm not going to get into how I'm doing this, because this is futuristic, but I factored it, I'd have x plus 1, x minus 2, and x minus 3. Let's think about the similarity. This parent function only has 1, 0. This graph has 3, so you can equal 0. So let's remove this graph and think about how I can create this graph with the knowledge of what the parent function was doing. So let's get rid of that. And let's plot the zeros at -1, 2, and 3. Remember, if I use the zero product property and individually set these equal to 0, I'll get a 0 at -1, 2, and 3. So let's plot those points. If I was thinking about graphing this just from what I understood from this graph, I would say to myself, well, it has to start down here, because the parent function did this. This was the parent function. But this graph is going to have to start down here and hit this point. Now think about it. It actually has to come back and hit that point. So it's probably going to come up at some point and have to come back down and hit that point. And then once it comes through here, it has to go through that point. So it's going to go like that. So this graph is going to do something like that. Now, don't graph this on a graphing calculator and blow up my email that it's wrong. This is just a sketch of what it could look like. And because this is an inequality, remember, we just walked away from inequalities. And I said, you know what? There's a shortcut to this process if I understood what the graph looked like. This greater than or equal is simply saying, when is this above the x-axis? Well, I can look at it and tell you where it's above right now. It's above it here and there. This means the answer to this third degree inequality is right there. If I knew something about this parent function, it helped me graph it, And because I knew something about the graph, I was able to answer this in interval notation simply by understanding the graph. Greater than above the x-axis. Remember, all greater than is really saying is, where am I positive? I'm positive up here. I'm positive up here. Down here, I was negative. Down here, I'm negative. Those don't work. Now, if you went to your textbook, you would have done something like that, right? It would have made you take these 3 zeros, plot them. It would have made you find these regions. You would have had to test each region. But ultimately, all you were really doing is saying, where am I positive? Where am I above the x-axis? Where am I positive? Where am I above the x-axis? And you can see from this would have been the solution region, and that would have been the solution region. But I was able to answer this question without doing any of this because I knew something about what this graph looked like and what this graph could look like based on what the behavior of that function was doing. So again, that's beyond this lesson. I just really important that you don't just write this down and then forget about it. Truly understand that I'm almost pleading with you that these 10 parent functions are something that you want to burn into your brain, maybe even put in flashcards and truly know what they look like so that when we get into third degree polynomials and square roots and cube roots and absolute values and reciprocal functions, that you have memory of their parent functions that will aid you in any transformations that we're going to work with. Okay? So there we go. Take the notes and have a great day.